Pantheon AI presents the big issue with solving Navier-Stokes. All right, Sarah, let's dive into something that sounds incredibly complex, but is actually all around us, the Navier-Stokes equations.
Okay, I'm ready. I know they have to do with fluids, like water and air, but that's about the extent of my knowledge. They're fundamental for everything, right? Weather, airplanes.
Exactly. They describe how fluids flow. They're the bedrock of fluid dynamics, written down way back in the 19th century. But here's the kicker, and the reason we're talking about them today.
Oh, I sense a mystery coming.
A big one. We haven't actually, fully solved them in a mathematical sense. In fact, proving one specific thing about them is one of the 7 Millennium Prize problems.
Wait, one of those problems? The ones with the $1 million prize from the Clay Mathematics Institute? For an equation from the 1800s? What could possibly be left to solve?
That's the $1 million question, literally. So, at their core, the equations are about two main things, conservation of momentum and conservation of mass. Think of it as tracking where every little bit of fluid is going and how much push it has.
Okay, that seems logical. Like a cosmic accounting system for water.
A perfect analogy. But the problem isn't about the accounting. The Millennium problem asks something very specific. In simple terms, if you start with a nice, smooth, well-behaved fluid, are you guaranteed that it will stay smooth and well-behaved forever?
Or what's the alternative? What's the scary version?
The scary version is what mathematicians call a, quote, blow-up. Could the fluid, in a finite amount of time, suddenly develop a point of infinite velocity or pressure? Could it just break the math?
Whoa. So you're saying a perfectly normal flow of water could, theoretically, have a single point that suddenly goes infinitely fast? That seems impossible. Why is that even a question?
Well, it comes down to a few incredibly tricky things in the math. The biggest culprit is a term that's nonlinear. It's called the convective term.
Nonlinear. Okay, break that down for me. Does that mean it's unpredictable?
Essentially, yes. It means the fluid's own velocity affects itself. It creates a feedback loop. A small change can get amplified into a huge one. It's the mathematical seed of turbulence.
Ah, turbulence. Now that's a word I understand. That chaotic, messy, unpredictable motion. So this one little piece of the equation is what generates all that chaos.
It's the main driver, and this gets even harder in 3D. Fun fact, in 2D, we times have solved this. We can prove that 2D flows always stay smooth. But add that third dimension, and all bets are off. The complexity just explodes.
That's fascinating. Just one more dimension opens up the possibility of infinity. So is it just the nonlinearity and the 3D space?
Those are the big ones, but they lead to other problems. For instance, we can't prove that the total energy in a system stays contained. If the energy at a single point could spike to infinity, that's your blow-up right there. We just lack the mathematical tools to put an upper limit on it.
So let's say someone solves this. What do we get, besides $1 million in bragging rights? Does it change anything in the real world?
It would be monumental. If they prove the solutions are always smooth, it confirms our mathematical models of the universe are solid, that they don't break. But if they find a counterexample, a situation where it does blow up,
then our understanding is wrong? Or at least incomplete.
Exactly. It would mean our equations fail under certain extreme conditions, and we'd need new physics to describe what happens. It would be a revolution in understanding things like explosions, or even the physics near black holes.
This brings up an obvious question for me, though. Why can't we just use a supercomputer? Simulate a bunch of fluid flows and just wait to see if one blows up?
That's what everyone asks. The problem is, simulations are, by nature, approximations. They chop up space and time into a grid. But the mathematical question is about a continuous, perfectly smooth space. A simulation might miss a singularity that happens between its grid points.
Right. The simulation could be too blurry, in a sense, to see the one pixel that goes infinite.
Perfect way to put it. Plus, the sheer detail needed to properly simulate turbulence is beyond even our best supercomputers. We can't get fine enough resolution to be certain.
So, to sum it all up, we have these fundamental equations that run our world. But we don't know for sure if they have a hidden self-destruct button baked into them because of nonlinearity and the chaos of 3D turbulence.
That's it in a nutshell. The big open question is, do the Navier-Stokes equations always work? or can they fail catastrophically? Solving it would be one of the greatest achievements in mathematical physics.
Pantheon AI, your information co-pilot.
Because learning shouldn't feel like a full-time job. Take care and see you next time.